Okay, so just a quick recap of watersheds that we spent a little more time on. This is still our lesson 8 on pore throat networks. So basically, you can apply watersheds. Watershed transform is kind of, again, we said like first you need a Euclidean distance transform where your distance is from the opposite phase, whichever phase you're working in. And then you have these layers that you're peeling off your object. And if you can imagine those distances, if you were plotting them, you will plot sort of a function, like a height function above your object, in 2 dimensions anyway. If you just flip that over, if you imagine that they're negative, okay, inside the object, then basically you would have these valleys, right? And those valleys are watersheds. So if you're filling up water and you start from the bottom, from those minima, you start from the local minima and you start filling up water from the local minima, you can start imagining that these water levels are going to merge from different regions. And at that merging point, you declare, okay, this is the boundary of my object. So that's how you split things into regions. And basically, you can either do the grain partitioning. This is an example from sandstone from Karsten Thompson. Karsten Thompson is former advisor of Dr. Balhoff. So if you're working with Dr. Balhoff, this would be your academic grandfather at LSU. so he's not that old, but anyway. And the other algorithms that I'm suggesting for the pore space partitioning are from ANU being Australian National University Group. They've done a lot of work in image analysis, and they have some of the most advanced codes. However, those codes are available only to their consortium, really. So basically, I can either partition grains into separate grains or pores into separate pores. Works rather well for sphere packs. However, for sandstones or something that might have a little more edges and irregular geometries, we have to be really careful, possibly merge afterwards. Or beforehand, I might be very selective about which minima I start from. So I might actually want to filter first my minima before I actually proceed into watershed. But other than that, a useful algorithm. Okay. Now, another one that is quite famous because it's also conceptually a very appealing idea. I personally, in practice, it's a little difficult to actually get the actual object of a throat object, rather. You can get pores rather well, but throats not so well. So I tend to prefer watersheds between the two, but it's a catchy idea. Here it is. We again actually need this distance transform, or rather for every voxel, I need what is the radius of the inscribed sphere. And then I imagine that I place a sphere inscribed into the object, in this case, pore space. So I imagine that at every voxel, I place a sphere. Now, locally, this sphere is one of the largest ones. And if I look at this pixel, whose center is here, it has a smaller sphere. I'm going to then declare, so I could either have the entire sphere with the pixel kind of swallowed by this larger ones, or they intersect. And if I have a smaller sphere next to a larger sphere, I'm going to declare that this one is the slave of this master. And I'm going to recursively, it's kind of, I guess, an appealing idea. And this one will then, and I'm just going to recursively continue that process. And then I'm going to have these big master spheres that have a whole lot of this subordinates. I'm going to call them subordinates. I don't like the word slave. So basically, there's this hierarchy relationship, right? But some of them I won't be able, because if this sphere, and there is, so for instance, there's this one and this one over there, they don't intersect. So they all will have a whole this agglomerate of subordinate spheres, but they themselves don't intersect. Then they're going to be two independent masters. Okay, so those are my pores. Okay, and where will I find throats? Throats are somewhere in between. So is the process basically this sphere here? Let's say that this is locally the largest sphere. All of the smaller ones, so for instance, point here has a much smaller inscribed sphere, right? It's going to get just swallowed. Actually, just if it's completely contained in this sphere, it's just going to disappear. However, if they're intersecting, like this one and this one, they're intersecting, they're overlapping. There is some of this smaller sphere that is basically outside of the larger one. Then I'm just going to declare that this is subordinate of the master. Okay, and basically then my pore space surrounding this sphere is the agglomerate or intersection of all of these spheres that are kind of together. Now that's my one pore, and then my second pore is over here, and the way I find the throat is say, oh, okay, I have basically two spheres from both of these clubs that intersect. Okay, so as an intersection of those, I'm going to declare a throat. Okay, so the smaller ones might intersect even though the masters don't intersect. Okay, so that's where a throat position is. Now, getting actual throat as an object might be difficult in this process. It might not have this feature of having a stop-gap filling voxels that I sometimes need. Okay, I have to kind of rely on these spheres to declare where the pore spaces are, but I can know the radius of the throat and its approximate position, and that might be everything that I need for a pore network model. So good enough. But if I want to characterize and say, well, what is the shape of this throat, that's going to be difficult with this approach. So that's basically it. So this is an example pore space after only sort of masters are left. Okay. I can do drainage and inhibition based on this maximum Bose network because I take the radius of these master spheres as my basically being radius of an interface at that point, so I can relate it to the capillary pressure needed to overcome. And for drainage, that works well. Frankly, everything works for drainage. So if you come up with a great method for drainage, I'm not going to write home to my mother, hey, there's a student here who came up with a great drainage simulation, okay? However, for inhibition, I might write a letter to my mom, okay? So if you want to work on something challenging, I would work on inhibition rather than drainage. Pretty much anything works for drainage, seriously. So you can get a pretty good match with the experiments as well. So overall, just to kind of wrap up, if you have images, you could just go and characterize pore spaces and get a whole lot of statistics of pores and throats. And you can use that as comparison between different media, okay? So you can just spend a whole lot of time just like comparing and characterizing. You could build a network from there, and you could either use an actual network or try to do some stochastic realization, in which case you would come up with 10,000 similar networks and do a little bit of uncertainty quantification on that. Either way, the network flow I call network flow modeling some sort of semi-upscaled, because this process of creating the network, you're gonna leave some details behind. Some details of the pore space are left behind, and the simulation is actually simplified. So I call that semi-upscaled situation. And basically that will give you the parameters that you might want to, certain parameters that are defined macroscopically, such as capillary pressure saturation or relative permeability, again related to saturation, permeability. So those are what we call macroscopic parameters. Those are the ones that you can also compare with whatever imaging you have of the fluids in the pore space. So you don't have to go through the network modeling. You can actually go and look at pore spaces directly. Okay? Either way, no matter what you do, you kind of want to come up with this predictive modeling on the core scale. Okay? And having both images of fluid distributions and pursuing the modeling in itself, you kind of want to compare the two or trust your modeling and then move on. And then with modeling, you tend to do much more than, or you go into details that you wouldn't go in the lab. So things go, what I want to communicate is that things go hand in hand. Okay, things are not independent. So that's, and this is just a quick example that is not important. Review papers. This is by now an outdated paper by Martin Blunt. This is a more recent one by Wahid Jokarni Asar. He is now faculty somewhere in the UK. And then these are selected papers from my research group that are targeted for unconventionals. So I've been using pore network modeling mostly for unconventional media. A lot of you might know Ayaz. He's still hanging around in the department as a postdoc, and Rui is sitting right down there. He's been using these same network models for absorption modeling in unconventionals. And that is it for network modeling. And we're going to move on and start the new topic. And that is lattice-Boltzmann methods. So there is an entire school of thought that says you don't need to do any network modeling. Okay? You can just image. We have these days beautiful images, porous materials, and go from there directly. My school of thought is that at different times you need to do different things. I would love to just image in 3D and do direct modeling, however many cores I need in Texas Advanced Computing Center. However, I might have unconventionals, and that's what I thought until Shell came along. Okay? You might have either a difficult carbonate or unconventionals on your hand, and no matter what you image it with, you don't have enough resolution. That's a problem number one. Problem number two, whatever you image it with in 3D might not give you a connected pore space to work with. So all of the fancy modeling of single phase, two phase flow, you name it, ain't gonna work. You don't have a connected network. Okay? So Rui, I'm gonna pick on Rui today. He's like, why me? Because if you do a lot of unconventional modeling, you're gonna do SEM imaging, and SEM imaging does not provide you with a 3D pore space. So you have to figure out a way to translate. And in that case, pore network models might be more helpful. They're also faster. So you can execute, and I'm going to share the table. So recently, aforementioned Rahul, as part of his PhD thesis, is looking into the literature review. And we basically put together, so we're like, let's do a table of network modeling methods and these lattice-Boltzmann methods and direct modeling methods, right? So basically the table on network has something like 5-6 pages long, okay? And you can see that it's much easier to play with. It's a faster simulation. It has certain simplicity conceptually. It's easier to develop one. If I really pushed you hard, you would be able to sit down and have a working code by Monday. Okay, that's useful. Even if it's too simple, that's useful because that extends your thinking and you can start playing with scenarios. Okay? So you will see, you can see, and I can share that again, and I will share that entire table just for you to see what are and in terms of the different physics that can be introduced. Even though it's not exact, again, it's easier to play with. So much more difficult things are possible then, or much more complex transport processes have been modeled with network modeling than they were with direct modeling. With direct modeling, you have less parameters to fit, but you might not have enough time on your hands to graduate in time, right? And produce, because in order to bring conclusions, you have to have enough simulations run to start comparing. That's just the reality, right? Otherwise, you present two simulations and, right, everybody will find their problem with the simulation. So you have to, in order to have conclusions, you need to have enough cases then. So in that case, that table is way shorter, right? Precisely for the running time, computational time reason. I personally don't like introducing parameters, and I do have problem often with network modeling flow when I don't know how to. Let's say that I want to model particulate flow through a network. You have to come up with this ad hoc rules, and nobody has come up with good rules, really, for how particles that are similar to the throat sizes clog throats, and how does that propagate through the network. So there are certain ad hoc rules, whereas with the more direct methods, you don't have to come up with ad hoc rules. But for certain cases, for instance, three-phase flow modeling, I don't know of anyone who's done in 3D on a decent REV. Okay? Even though the same lattice-Boltzmann method, its extension for 3 phases is valid, it's just it's computationally intractable right now. Okay? So, or maybe it would be computationally tractable, but whoever can actually do it didn't get to it. Okay? So in that sense, there is a benefit in having simpler methods. Never criticize really how sometimes methods are too simple. Criticize the conclusions brought by those. You can still, even with a simple method, you can use it as a vehicle, okay, for your understanding regardless. So you need to have a number of methods at your disposal. So with that long introduction, let me introduce you to lattice-Boltzmann methods. If you need a book, there are 2 books. This introductory book, I would say it's possibly too simple. There's another, the language is really simplified. It's a true introduction, which is a good thing. This one is a little better. There's actually another one from 2007. You might know the title. It's also Sukop, right? Yeah. So there's another follow-up of this one that is a little more recent than. Is that by Wong? No, Sukop at all? I think he was one of the authors. Yeah. In any event, there's plenty of books on lattice-Boltzmann modeling. It's really popular. There's also a PhD thesis, as many as you'd like. So here's the basic idea. Here's my pore space. This is where the white voxels are. And the green, shaded green, are my grain spaces. And if I imagine physical gas, this would be sort of a box, and I would have these molecules of gas moving around in all kinds of directions. Kinetic theory, anyone? Does that ring a bell? All right. So imagine such molecules bouncing around. Now, what we're gonna put this on a grid. I'm gonna say, okay, these molecules can't just move in all directions. I'm going to give them a set of discrete possible directions they can move in. Okay? So I'm gonna imagine in this particular case, for 3 dimensions, this is so-called D3Q19. Okay? I can sit in the same place, or I can move in any of the possible other 18 connections. Remember 18 connectivity? What does 18 connectivity refer to? I am a neighbor to another voxel that I share an entire side with, or edge. Okay? Box, 2 little boxes sharing an edge. Okay? If I share just a corner, I need not apply. That's 26 connectivity. Okay? So equivalent, and this is, so it's 18 plus 1, 1 being the one in the middle that's not going anywhere. So 0 velocity. Okay? So I could also have D3Q27 for some mysterious reason is not numerically stable. You will never see actually D3Q27 used. Okay, D3Q19 is the most common method. So I discretize my world of velocities and at every point I imagine that I have a whole bunch of gas in there, and this actually started literally from what's called cellular automata that were bouncing balls, okay, individual balls. But here I'm not going to bounce balls, I'm going to bounce particle swarms or distributions. So I'm going to say, okay, for each of these directions, I have a distribution of particles going in that direction. And when I sum up all of those distributions, I'm going to get density of gas at that spot. Okay? It's sort of like a probability. Probability, if I divided my distribution by the entire density, I would get a probability of gas in that direction going in that particular direction. Okay? So other than that, so I need to, and I do this at every node that is inside the pore space. I don't do anything. I don't do computation on the nodes that are in the solid space, except for these that are marked here as yellow. Those are my so-called bounce back nodes. So they're like just like I have kinetic theory, if I hit that boundary, I'm going to bounce back. Now, of course, there's multiple ways. There's zillion boundary conditions out there. We're going to mention the simplest one, where if you hit this way, you actually imagine like you're going to go towards this solid node, and it's going to just reflect back the way it came from. Okay. All right. So just prepare. Let's say that I asked you to prepare for simulation in Fiji and image J, and you take a segmented image. Here's our favorite disk pack. And I would like you to, how would you identify bounce back nodes in image J using methods that we've used in this course? I want, again, these borders. So every grain voxel that is bordering a pore voxel, I want it colored differently, labeled differently, you name it. How do I get them? Okay, I could do edge finding algorithm. Okay, that's one way. So gradient is really high between those two, except that my problem is that gradient will be high at the pore space voxel near this boundary, and so both of them. And I want only, but I guess I could intersect them somehow, find high gradient.
What if you erode the image and subtract it?
Thank you. So erode grain space by one layer, or dilate pore space by one layer, however you want to look at it, and subtract the two, and this subtraction is this right now. Okay? So that is the fastest way to actually get. You could also go and query, hey, in the neighborhood of this pixel, do I have any one of the opposite phase? Okay? This could have been a quiz. Okay? We've been through this stuff. But it's getting quick at these queries, there is something in your image, is actually extremely important. It's somewhat trivial when you think about it. If you ever think about math, oh, where is intersection of two lines? Of course we know where the intersection of two lines is. Math says it's simple, right? Finding that intersection in an actual image is not so easy, right? Intersecting a ray of light, if you think, through your image, through the entire object, that might be complex, is not a trivial question. So being quick in applying these algorithms to identify certain portions of your medium is actually important if you want to characterize. Yes, question? There was a question about it. Yeah.
So you have found the boundaries of the grain, but what about the spaces in which I don't have any black color? So for example, the left corner, down left corner.
This one?
Yeah.
So what about it?
No, the white part in
This one?
Yes.
It doesn't bounce back. So now that is your other boundary. So that's not your wall boundary. So in every modeling method, you're going to have a wall boundary, as in fluid-solid interaction, and you're going to have an actual boundary condition, okay? And this is the volume boundary condition. So unless you decide to, so what we typically do in simulation, conceptually and otherwise, you're going to seal all image sides except for the two that you're coming in and out, okay? And on in and out, you're going to have to set something, either these densities that I'm going to get to, or there's velocity, okay? So those are your options in any kind of flow type of models. Velocity or the gradient of the velocity. All right. So if I had a 2D world, then I would have a so-called D2Q9 lattice. And this is an example of it. So basically, these are my possible 9 directions in 2D, okay? Including the one that is like sitting. Uh-oh, my MathWorks has, MATLAB has died again. I'm gonna have to restart it, but oh well. So anyway, my MATLAB and projectors. MATLAB, PowerPoint, and projector together are deadly combinations. All right. But only after a certain number of hours. I've had them open since this morning, and I taught the first class without the problem. And in the afternoon class, that same MATLAB that has been open since morning dies. This is like a pattern, actually, daily pattern, or Monday, Wednesday, Friday when I teach. So I might have, so this is, for instance, for my, okay, it is, ignore, bye. Okay. This is my distributions, and I'm going to call them Fi. So I have F0, or a fraction or a distribution of F0 staying here, not moving anywhere. And then I have fraction of F1 in this direction. So this is my vector E1. This is my vector E2. Okay, this is the fraction. And I keep going. Okay. And my, what I refer to as density, this is in lattice. These things are normalized, of course. Whenever you have a numerical method, your numbers better be close to 1. Do not go into numbers that are straying much away, because your numerical error will pile up. Okay? So this is normalized in so-called lattice units. So this normalized density will be sum of all of these fractions. And that's also known as first moment. Okay? And then your velocity is basically this weighted sum of all of the, so I know if this many particles are going in this direction, right? I sum up all of those moments, and I divide it by the density or sum of all of these fractions. So it's sort of like a weighted sum. Yes?
Where do you get the distribution from?
You start with 0, okay? And we're going to see how it actually starts moving, okay, in a second. So this graph is showing all of my possible velocities at this voxel or pixel, okay? I have 9 possible velocities if I'm in 2 dimensions.
Why are they different lengths?
And they're different lengths. They're actually going different lengths because I'm supposed to approach this other voxel and go to the boundary. So these velocities actually are, so that's good observation. They're not all the same length 1, okay? This one could be, I would call it 1, and this one is square root of 2. Okay? So, and that's fine as long as we always have the same set and we normalize them. Okay. Now, what we do in this so-called single relaxation time, which is the most common or the default method that if I asked you to program, you would again probably program in 2D by Monday. Or rather program by the end of tonight and then debug by Monday. We know how that works, right?
You can do it in 10 lines in MATLAB.
Right. So yeah, it's quick programming. What you do is the following. So you kind of, at every node, I compute how much of me is going in which direction, okay? And then after I compute that, that's called streaming. And after that, I collide. Then I send them out, okay? And I send the contributions from every voxel to all of these neighbors, okay? Based on these velocities and fractions. So at my next step, t plus delta t, okay? Basically, this is my value of Fi at the next step in the direction. If this is, so this is a step at the location. So if I'm sitting here, okay, then let's say that my E1 is this one, okay? F of x plus E1 plus delta t is basically my neighbor down there, and that's where I'm sending my fraction right now, okay? Minus the current value of this is basically I'm relaxing towards what we call equilibrium, and for equilibrium we simply have a formula, so all of these things are known and can be computed. I didn't list what these weights are, but they're given weights, okay? And basically I send them out and just I look at how far am I from my anticipated equilibrium, and I try to kind of push myself and get there in a very linear way, just like this is coefficient tau is a given coefficient, okay? So in some sort of a linear gradient approach way, I'm trying to approach my equilibrium. And I keep doing this, okay? Until I don't see a lot of differences between two subsequent steps, meaning that I arrived at my equilibrium. Now, how do I get these weights? Just like in any finite difference method out there, you're gonna do your Taylor series on, this is actually a discretization of a specific differential equation. You're gonna do your Taylor series, and you're gonna make sure that these weights ensure that it's first order, second order, or whatever order method that you have. So basically those powers in the first and second order will disappear, or you're gonna set the weights to be disappearing. That's how, for instance, central differencing for first order derivative works anyway, right? So you can prove that you use Taylor series through and through. If I'm speaking in a foreign language, that means you need to take a numerical methods class. So go to Dr. Sepernori and take the one on finite differences, okay? If not, just let it slide for now. It doesn't matter. It's a standard way we come up with numerical methods. You don't need to understand how convergence of numerical methods works to actually implement this or use this, okay? Now, the way this function is set up, this equilibrium, there's actually, and that kind of analysis goes way above my head too. I never really went into a lot of details, but basically, if and when you get to the equilibrium, okay, given certain limits on the time step and also this delta x and delta t and so forth, it's actually proven that you will arrive to Navier-Stokes solution, at least for lower Reynolds numbers, which is what we're after most of the time in forest meeting. So even though this equation is it's actually Boltzmann equation, it's not Navier-Stokes equation. I'm not discretizing Navier-Stokes equation. Navier-Stokes is way uglier. Okay? I'm sorry, complex, non-linear, right? This is actually a way simpler equation, but in the simple rules of things bouncing around, which mimic kinetic theory, I actually arrive at the correct behavior, which is amazing. And it arrives from these collisions and interactions. So there is more stable. So simplest method is always the most appealing, the simplest to implement, but of course not the best behaving ever, though this works in most cases. For better convergence and more stable behavior, you need to go to multiple relaxation time. There is a couple of more parameters, not just tau, to choose, okay? And there's an entire matrix of parameters, so you actually have to do a matrix times the differences, and so it becomes just a little more involved. Again, if I gave you another weekend, you would program this too, because the table is available, you just program it, okay? And you might have some forcing, we didn't discuss that, so actually I think that's the next, oh, this is this, so I come up with what my current, who am I sending in which direction and what fraction, and then I send them there, okay? I bounce those contributions in the correct direction, and I just sum up. So basically this node over here is going to get this contribution, but it's going to get all other contributions in this colliding step. It's going to get all other contributions as well. Okay? You just go to every voxel and let them send things off and just wait for to go through everyone. What's nice about this is that it's pretty local. I can do this and I can just do this set of nodes with one core and this other set of nodes and the other, and work independently. So you will often hear this word that lattice Boltzmann is very parallelizable. Okay? I don't need any more information other than my neighbor in voxel, which is great. Okay? So I can work independently with multiple cores on the same image at the same time, and then just make sure that, of course, at the matching part, yes, you still communicate, but that's not a lot. Okay, it's relatively simple. All right, and then there's this bounce back wall. So basically, if I were bouncing, these are my solid nodes, and these are the ones that we just identified in Fiji and all that. So if I actually hit the node like that, then I basically just put back in. And it works well. It works really well for straight walls. Everything works really well for straight walls. But the formulations for curved walls are actually not all that more complex, and you can get pretty good behavior. Okay, so I'm going to actually demo this, and hopefully, oh, I'm going to have that MATLAB that died. I can maybe just let you download it next time, but I'm going to attempt. So at least what I want you to do is go on MATLAB Central. So actually just go and download it for today, and we're going to continue next time. So there's so-called LBM demo by Sébastien Leclerc on MATLAB Central Exchange. So just go and find it. It's a little cute visualization of this streaming and colliding. Leclerc, Sébastien Leclerc. So when you download it and then so basically it kind of runs in parallel and tells you how. So first you have all of these velocities, and you kind of stream, and then you collide and send them back. And we will see in this figure, this is how overall velocity, the one that you compute, starts evolving. Streaming in all directions for everyone at the same time. And this is now my overall velocity, which is some weighted sum of all of the other velocities. Then I repeat. So the bounce back is necessary. Then I'm streaming. So that rotating visualization was like visualization of streaming. This one. And then these will adjust slightly, okay? And you will actually see how, like, if you let this run a little, you will actually see, amazingly, the simple process will actually start forming the velocity you would expect for this image if you had a no slip, right, boundary condition and the fluid in there. So these will keep adjusting right there, see? So eventually you will kind of go properly around this corner and your velocity will be small here and much bigger in the middle of the pore space. So just to get the feeling of how the lattice Boltzmann works. And all from bouncing balls around. A whole lot of modeling goes by bouncing balls around. You will notice. Okay? Yeah. I'm going to disconnect before my MATLAB disconnects anyway. All right. So give it a try, download it, give it a try. We're going to try it again at the beginning of the class next time before.